Welcome to Quantum, the channel where we explore the mathematical, theoretical, and philosophical foundations of physics. Today's lecture offers a concise yet insightful discussion on the connection between the renormalization group, RG equations, and phase diagrams, using the Ising model as our guiding framework. In particular, we'll revisit one of the oldest and most illuminating RG techniques, the Migdal-Kadanoff MK approximation. Through this method, we'll uncover the structure of fixed points and the rich phase behavior of the Ising system. This lecture is structured into 5 sections: Kadanoff's block spin prescription for the Ising model, the Migdal-Kadanoff RG approximation, the MK decimation rule in one dimension, a summary of the MK-RG scheme for the Ising model, and finally, a detailed look at the fixed points and phase diagram of the 2D Ising model. Let's begin. Kadanoff block spin prescription for the Ising model. In the Kadanoff prescription, we study phase transitions by grouping neighboring spins into blocks. Each block becomes a single block spin based on the majority rule. This simplifies the lattice while preserving large-scale behavior. The new block spin system has a similar Hamiltonian, but with rescaled couplings. Repeating this blocking defines an RG flow, and at the fixed point, the system becomes scale invariant. This idea explains universality. Different systems with different microscopic details show the same critical behavior near phase transitions. Migdal-Kadanoff RG approximation. The Migdal-Kadanoff renormalization group is a smart approximation for studying phase transitions in lattice systems like the Ising model. It works in 3 steps. First, we keep only regularly spaced spins, reducing the number by a factor that depends on the blocking size and the dimension. Second, we move internal bonds outward so that interaction energy is concentrated between retained spins. Third, we rescale the couplings to preserve total energy. The result is a simplified, coarse-grained system that still captures critical behavior through an effective RG flow. MK decimation rule in one dimension. In one dimension, the Migdal-Kadanoff decimation is exact. We keep every bth spin, that is, every spin number that is a multiple of b, and integrate out the rest. The renormalized interaction becomes the original coupling raised to the power b. This gives 2 fixed points, 0 for disorder and 1 for perfect order. But only disorder is stable. That's why the 1D Ising model has no phase transition. Thermal noise always dominates. MK-RG of the Ising model. A summary. The Migdal-Kadanoff method simplifies real space renormalization by combining 2 steps, bond moving and decimation. In bond moving, we shift interaction energy onto the spins we keep, amplifying bond strength by a factor of b to the power d-1. Then, in decimation, disconnected spins are removed, and the remaining one-dimensional chains are solved exactly. The result is a rescaled Hamiltonian that preserves essential physics and predicts critical behavior with surprising accuracy, especially near phase transitions. Fixed points and phase diagram of the 2D Ising model. In the 2-dimensional Ising model, the Migdal-Kadanoff method tracks how the coupling constant t evolves under coarse graining. The renormalization function maps t to 4t squared over 1 plus t squared squared, revealing 3 fixed points, 0, 1, and a critical point near 0.296. This middle point, the Wilson-Fisher fixed point, marks the phase transition. The method predicts a critical exponent nu around 1.34, close to the exact value. It captures how universal behavior emerges near criticality, even from approximate flows. That wraps up today's lecture on the Migdal-Kadanoff RG and its connection to the phase diagram of the Ising model. We've seen how RG flows reveal deep structure beneath critical phenomena and phase transitions. As everybody knows, the Ising model defines the so-called Ising universality class, which describes all second-order phase transitions and is fundamentally captured by the phi-4 field theory and its Wilson-Fisher fixed point. The renormalization group is more than just a tool. It is the meta-framework, the theoretical foundation, and the computational engine behind all of quantum field theory. The Ising model and RG thus bridge 2 worlds: the phase diagrams and critical exponents of condensed matter physics, and the renormalizability, continuum limits, and existence questions of QFT. If you found this insightful, consider subscribing to Quantum, where we explore the frontiers of theoretical and philosophical physics. Until next time, stay curious and keep thinking deeply.